Let's talk now about exponential functions. Normally I begin with some definition or some problem, but here let's begin with a visual. Let's start off with a penny. All right, so now a penny is not a lot of money. It's 1 penny. It's exactly 1 cent. But now I'm going to perform some actions to make this money grow. All right, so here's going to be my first action. The first thing I'm going to do is I'm going to double the amount of money that I have. Well, that's going to bring me to 2 pennies. Okay. The second thing I'm going to do is I'm going to double this money again. That's going to bring me to 4 pennies. The third action that I'm going to take is I'm going to double this money again. And well, doubling 4 gives me 8. And the fourth action that I'm going to take is I'm going to double this money again. Notice every time I take an action, the result is I'm going to double the amount of money that I currently have. Okay. Now, after 4 actions, I went from, I have 1 penny. The first action gives me 2. The second action gives me 4. The third action gives me 8. And the fourth action gives me 16. Now, this may not seem like a lot, but if we continue this trend, if we continue this pattern, the amount of money will grow very, very quickly. This is an example of what's called exponential growth. Now, how quickly does it grow? Well, I don't exactly have this many pennies, so let's go ahead and look at it as a list. Again, we started off with 1 penny, and then that became 2, and then 4, and then 8, and then 16. If we continue that pattern, doubling 16 gives us 32, and then 64, and eventually we get something that looks like this. Note that, again, we started off, no actions had been taken, we just had a single penny. After 1 action, after 1 doubling, I had 2 pennies. A second action doubles my money again to 4 pennies. A third action doubles my money again to 8 pennies, then 16. That's where we left off in the visual. But if you keep going, you end up with 32, 64, and 128. Notice it takes me 7 actions to get to 128 cents, $1.28. But once you get past that, you're going to notice it starts to grow very quickly. You next have $2.56, $5.12, $10.24, $20.48, $40.96, $81.92, and as you keep doubling, you go into the hundreds, then into the thousands, then the 10,000s. So that by the time you're done, now remember these are pennies, so these last 2 are in cents, but by the time you're done, you're left with $2,684,354.46. So just over $2.5 million. That's after doubling your money only 28 times. So if you started with it today and you went through to the end of February, then you would be able to say, oh, by the end of February, I turned my 1 penny into just over $2.5 million. Right? Now, this is an example of what's called exponential growth. And that's what we're talking about in this section. We're talking about functions that behave this way, that allow the input, that allow the values of x to grow, that allow the values of y to grow this quickly based off of your x value increasing. All right, so let's go ahead and take a look at a little bit more formally how we define that and how we want to talk about that. All right, so let's go ahead and take this away. All right, so let's define the phrase that I just mentioned. Let's begin this section with a definition. All right, definition. Let's start off with a number. Let's let A be some number that's positive. We're not going to want any negative numbers, which we'll see here in a moment. Let A be a real number such that A is greater than 0. Okay? Or if you could also say let A be any positive real number. Either of those is fine. Let A be a real number such that it's positive, or just let A be a positive real number. Okay? Let's go ahead and we're going to accept any positive number except for the number 1. Why not the number 1? We'll see that as well in just a moment. And A is not equal to 1. Okay? Then a function of the type f of x equals a to the power of x is an exponential function. With the base of a. Depending on what your base is, you'll have a different exponential function, so we do specify that in the name. Right? Note that you're usually used to seeing a variable as the base and the power as a constant. So think about a quadratic. You're usually used to seeing things like this. F of x is equal to x to the second power. Notice here your variable is the base. The power is just a regular number. It's the number 2, the constant. Okay? This is not exponential. This is a quadratic. What an exponential function is the other way around. If you have f of x is equal to 2 to the power of x, now you have your base is just a regular real number. Now remember, you don't use negative numbers, you only stick with positive numbers, and you don't use 1. Your power, that's a variable. All right, so this is what we mean when we say an exponential function. Now this base can be any real number other than, it can be any positive real number other than 1. You could say 3 to the x, 4 to the x, 5 to the x. You can use a decimal if you like. You could say 0.3 to the x. You could use a fraction. You could say 1/2 to the x. All of these are examples of exponential functions. So that's our definition. All right? So now let's go ahead and consider an exponential function in probably the simplest way that we can, and that's by considering its graph. So as our very first example, let's go ahead and take this one and graph it. Okay. Now, what I'm going to do is I'm going to substitute in values of x. All right, so let's go ahead and do that. We're going to say x is equal to some numbers, and from that, we're going to find out what our f of x is equal to. All right, so I'm going to start with 0. I'm going to put 0 right here. Why did I put it so far down? Because I'm going to use some positive numbers and some negative numbers. Now, you might say, well, wait a minute. I thought you said you can't use negatives. The base can't be negative. The power can be whatever we want. Positive, negative, fraction, whole number, decimal. That doesn't matter. It's the base that needs to be positive and not equal to 1. Okay? So here we go. 2 to the 0 power, well, that's equal to 1. In fact, anything to the 0 power is equal to 1. That's going to be very common because anything to the 0 power is equal to 1. That means that all of our exponential functions, whether it be 2 to the x, 3 to the x, or 1/8 to the x, they're all going to have 0, 1 in common. Okay. Now let's see what happens when x is 1. 2 to the power 1, well, that's just the number 2. If I say x is 2, 2 to the power 2, well, that's 4. And if I say x is equal to 3, well, 2 to the power of 3, 2 times 2 times 2, that's going to give us 8. Oh, those numbers look familiar. 0, 1, 1, 2, 2, 4, 3, 8. Those were exactly what we had in our problem over here, in our example with the coins. You have 0, 1, 1, 2, 2, 4, 3, 8. Remember what the pattern was here. Every time you take one more action, what's going to happen is your y value, the amount of money you have, is going to double. That pattern continues on and on and on forever. Well, think about it, what it means with respect to a function. With a function, what it means is every time your x goes up by 1, your y value gets multiplied by 2. It's going to double, times 2, times 2, and times 2. But what happens if I go backwards? You say, well, you already got to 0. Well, yeah, but we can have negative numbers. We can say -1 and -2 and -3. Well, notice, if every time I take a step forward, my money doubles, and doubles. What happens if I go backwards? Well, the opposite of doubling is being cut in half. Half of 8 is 4, half of 4 is 2, and half of 2 is 1. So if I keep that pattern going, half of 1, well, that's a half. And then half of a half, well, that's a fourth. And then half of a quarter, well, that's an eighth. Notice that these numbers are the same in the denominator as they are over here as whole numbers. These are reciprocals of each other. So 2, 1/2, 4, 1/4, 8, 1/8. Here the next one would be 16, as we saw in our example over here. The next one after 8 is 16, and then 32. So that means over this way, the next one would be 1/16 and 1/32. Okay? So here we have a nice pattern going. It's the same pattern as we had with the pennies, with the money. Now let's take a look at it graphically, and we'll see an even more prominent pattern emerge. So let's give this a try here. All right. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Let's see. 1, 2, 3, 4, 5, 6, 7, 8. Let me go up a little higher. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 1, 2, 3, like this. All right, so let's plot some points. 0, 1, well, that's the y-intercept. 0, 1 is on the y-axis. Okay. 1, 2, that's 1 to the right, up by 2. 2, 4. 3, 8. Let's see, 8 right there. If we go backwards, that's -1, 1/2. -2, 1/4, -3, 1/8. If you connect your dots, you'll notice that you have a nice smooth curve that emerges. You have a nice smooth curve that you draw out. Starting from the y-intercept, as you go to the right, it almost looks like a parabola. It almost looks like the graph of y equals x squared. But as you continue on to the left, you realize that it doesn't behave like a parabola. It doesn't go back up. It, in fact, flattens out to be a nice flat curve right above the x-axis. Now you say, what do you mean right above? If it keeps going down, doesn't it eventually hit the x-axis? Well, no. Because on the x-axis, your y value would be 0. And notice, these y values are not 0. Because the way I get the next y value is by cutting this one in half. And if I take a positive number, even if it's a very small positive number, and I cut it in half, I still have a positive number. And if I take that positive number and I cut it in half, it's going to be even smaller, but it's still going to be a positive number. So that means it's never going to reach 0. So here your graph follows the x-axis, but it never quite reaches it. It never actually touches the axis. It only follows right above it, just like this, right above the x-axis. On the right side, it goes up very, very quickly. This is an example of what's called an exponential growth curve. Notice that I said exponential growth. You say, well, I thought these were called exponential functions. What's the extra word for? Some exponential curves will go the opposite direction. Instead of getting very big, they'll start off very big and they'll get small really quickly. Those are called exponential decay, and we'll see those in just a moment. So here, let me go ahead and label this as exponential growth. They're all exponential functions. However, the graph will sometimes look one way, sometimes it'll look the other way, depending on some things about growth. I don't know how to spell. There we go. Growth. Depending on what the function itself is. All right. Let's do that again. Let's graph another curve. Let's go with, in fact, I'm going to ask you to try this. Go ahead and give this a try. Go ahead and graph f of x equals 3 to the power of x. I'm going to go ahead and graph it on this same curve just to compare. So as you're following along with your notes, you may want to actually graph it on the same curve, or you can use a different one. That's up to you. Go ahead and graph the same way. Go ahead and plot some points and see what happens. And as you're doing it, try and notice the same kind of patterns that I pointed out here. Go ahead and pause your video, give this a try, and once you're done creating a graph of f of x equals x to the third, go ahead and unpause and we'll go through it together. All right, so let's take a look. We're going to plot some values. We have x values and we have f of x. All right, I'm going to start with 0 right here. And again, as I mentioned before, any number to the 0 power is equal to 1. And that includes the number 3. Okay? So, what about if I use the first power? Well, 3 to the first power is 3. What if I use the second power? Well, 3 to the second power is 9. 3 times 3 is 9. What if I go the other direction? What if I say minus 1 and minus 2? Well, again, notice I have a pattern going. Here, when I increase my x value by 1, my y value gets multiplied by 3. If I multiply by 3 again, that gets me the next one. So every time I take one step forward, every time my x value gets 1 bigger, my y value triples. Oh, before with the number 2 it was doubling. With the number 3 it's tripling. That's what the base tells you. The base tells you every time your x value grows by 1, your y value will do that. It'll double, it'll triple. If this was 5 to the x, it would be multiplied times 5. If it was some decimal or some fraction, let's say it was 2.7, well then every time you added an 1 to your x value, your y value would be multiplied by 2.7. Whatever the base is tells you what happens to your y values. If you go backwards, then instead of multiplying by 3, you're dividing by 3. Okay, well, divide 9 by 3 is 3, yeah. Divide 3 by 3 is 1, okay. If I keep going, if I divide 1 by 3, that's going to give me 1 over 3. And if I divide this by 3, it's going to give me 1 over 9. Okay? Again, same pattern as before. Hey, look, I have my 0, 1, that's my y-intercept. And then everything here is the reciprocal of everything here. 3, 1/3, 9, 1/9, and it would keep on going in the same pattern. If I now graph these all together, look what happens. 0, 1 is still there. It's still the y-intercept. 1, 3, that's 1 to the right, up by 3. 2, 9, that's right by 2, up by 9. Negative 1, 1/3. Back 1, up 1/3, a little tiny bit, and then back 2, up 1/9. Notice that the points are in different places, but the pattern is still the same. You're going to cross through the intercept here, through the y-intercept. You're going to go up very, very quickly to the right. Notice it's going up even more quickly because over here you were only doubling. Now you're tripling, so it's going to grow even faster, so that it gets up higher. On this side, remember, but over here, you're cutting things in thirds. So it's going to get smaller even faster. So it'll get down close to the x-axis really quickly. But again, if I have a positive number and I divide it by 3, it's going to get smaller, but it's going to stay positive. So even with this one, even though it gets small very quickly, it still does not touch the x-axis. It follows right above it. So even if we have a different base, we still have a curve that looks the same. These are both exponential growth curves. Okay, now, you'll notice one thing we said before was do not use the number 1 as the base. Oh, well, why not? Well, look what happens if we try to use the number 1. So note, remember your base cannot be 1. Base cannot equal to 1. Why not? Well, let's see what happens. If I have f of x is equal to 1 to the power of x. Okay, well that's, let me choose some x values, and I'll find my f of x values. If x is equal to 0, well, anything to the 0 is equal to 1. Okay, all right. If x is equal to 1, well, 1 to the 1 is 1. If x is equal to 2. 1 to the 2, that's 1 times 1. It's also 1. What about 3? 1 to the 3rd. Well, that's 1 times 1 times 1. That's 1. What if I use a negative number? 1 to the minus 1. Yeah, that's also 1. These are all 1. So here, your graph never changes. It never grows. Because remember, what your base tells you is every time your x value increases by 1 step, your y value is going to be multiplied by this. By 2, it's going to double. By 3, it's going to triple. But if you're multiplying by 1, nothing ever changes. So here, this is not considered an exponential function. It's a constant function. A constant function is a function which never ever changes. It remains constant. And the graph of a constant function is just a horizontal line. So it doesn't follow this pattern, and therefore is not considered an exponential function. So note your base cannot equal to 1, should not equal to 1, because if it is equal to 1, then it's just a constant function. This, oops, I just switched to cursive. This is constant, not exponential. Okay. So we use any number other than 1. We also don't want to use negative numbers. Why not? It's actually not completely forbidden. It's not that you couldn't use negative numbers. It's that using negative numbers is a little complicated for us to use right now. Because this is an introduction to exponential functions, it turns out that negative numbers require you to do some math that we're just not going to get to right now. So if you have, for example, negative 2 to a power, there is a way of defining negative 2 raised to positive and negative and fractional power. It requires something that we can't really do right now. Right? It actually requires something that in the traditional course of things you would see either in a calculus class or something higher than that, something beyond that. So this restriction is there mostly because, well, if a is equal to 1, it's not going to follow any of these patterns. It's just going to be a constant. This one's there not because you couldn't have negative numbers, but because it requires something much more complicated than we ever get to in this course, right? Let's keep a positive, no negatives. And we don't use 0 for the same reason we don't use 1, because that would just be 0, 0, 0, 0 all the way down. Okay. Next, what we want to do is we want to consider what happens if I use a number less than 1. Because notice, so far I've seen why I shouldn't use 1, but my examples have all had a number greater than 1. What if I use a number less than 1? Now remember, it's still got to be positive. So when I say a number less than 1, I mean something like 1/2 or 1/3 or 2/5, some number between 0 and 1. Right? So let's consider the following example. Let's go ahead and graph f of x is equal to 1/2 to the power x. This is exponential because you have a positive real number here that's not equal to 1, and it's being raised to some variable power. So this still fits the same pattern as before. I could plot a few points, and now that I know how these patterns work for exponential functions, this doesn't take quite as long as you would think. Because after all, anything to the 0 power is equal to 1. And that includes this 1/2. Anything to the 0 is equal to 1. Okay, what about the rest? Well, remember, the way exponential functions work is anytime you take one step forward, you're multiplying your current y value by the base. So if I take one step forward, if my x value increases by 1, my y value is going to be multiplied by 1/2. Okay, well, 1 times 1/2 is 1/2. If I do that again, if my x value grows by 1, again, I'm going to multiply by 1/2. And 1/2 times 1/2 is 1/4. And if I do that again, my x value goes forward by 1. My y value will also be multiplied by 1/2. So 1/2 times 1/4 is 1/8. Well, wait a minute. I've seen these numbers. Those are these numbers down here. When I had 2 to the x, I had also 1/2, 1/4, 1/8. But notice that for 2 to the x, those numbers were what happened when I had a negative argument. But for 1/2 to the x, that's what's happening when I have a positive argument. That's going to mean something here very visually in just a moment. If I use some negative powers, now remember, every time I take a step forward, I cut things in half. So if I go backwards, well, then I'm doubling things. If I take 1/8 and I double it, I get 2/8, which is a quarter. If I double a quarter, I get 2 quarters, which is 1/2. If I double 1/2, I get 1. Okay, and if I keep going, double 1 gives me 2. Okay, that's that number. If I double 2, that gives me 4. Okay, that's that number. And double 4 gives me 8. It's the exact same numbers, but going backwards. So what does that look like? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. If x is equal to 0, y is equal to 1. Okay, well, no surprise there. Just like my previous graphs, it's going to cross through 0, 1. That's going to be common for every exponential function. When you have a base to the power of x, they're all going to cross through 0, 1, because anything to the 0 is equal to 1. Okay? Now, if x is equal to 1, y is a half. If x is equal to 2, y is a quarter. And if x is equal to 3, y is an eighth. Notice those numbers are getting smaller and smaller. But again, if I keep cutting things in half, they're going to get smaller, but they're never going to be 0. If I have a tiny, tiny number and I cut it in half, it's still going to have something left. So you're never quite going to reach 0. You're going to float right above 0 on down the line like that. It's going to float right above it. If I go back the other way, if I go to the left, -1, 2, -2, 4, -3, 8. And my graph goes up like this. Oops. Let's just pretend I hit that point. There we go. There is my graph. Notice, it's the same graph that I had before, but flipped around. This graph in red, this is 2 to the x. This graph over here is 1/2 to the x. They both cross here, but this one goes up to the right, down to the left. This one goes up to the left, down to the right. It's the same graph, but flipped around. Notice that instead of growing now, instead of having small numbers which get bigger and bigger and bigger as your x value grows, you have the exact opposite. Now your x values are getting smaller and smaller and smaller. They're flattening out. This is an example of what's called exponential decay. This is what happens whenever your base is less than 1. Because after all, if you're multiplying numbers by a number less than 1, they're going to get smaller. But if you multiply by numbers that are greater than 1, for example, 2 and 3 like we saw before, then you're going to get bigger. So what that does is it summarizes all of the graphs of an exponential function into only one of two possibilities. Sure, some minor details might change, but as an overall pattern, there's only two different graphs that you can ever get if you graph an exponential function. One graph will cross through 0, 1, go up to the right, and down, flattening out to the left. Like that. This is called exponential growth. Now, the details might be a little different, right? How high up does this go? That might change depending on what your specific function is, but the overall shape and pattern is going to look like this. This is what happens whenever your base is greater than 1. 2 to the x, 3 to the x. It doesn't even have to be a whole number. You could say 1.7 to the x. And that's fine. It'll grow like this. On the other hand, if your base is less than 1, then you'll have exponential decay. It's going to have the same pattern, but it's going to be flipped around. You're going to take this one, and you're going to flip it this way. This is exponential decay. And it's what happens whenever your base is less than 1. Now remember, your basis still has to be positive. So when you say less than 1, you mean between 0 and 1. And that's it. Those are the only two possibilities. Note that they both have the same intercept, 0, 1. Both exponential growth and decay graphs have 0, 1 as the y-intercept, they both go forever to the left and to the right, so that means their domain is all real numbers. In other words, you can plug in any x value. Notice I can plug in x is equal to 1, 2, 3, 4, 5, but also negative 1, 2, 3, 4, 5. And so here the domain is all real numbers. In interval notation, that's everything from negative infinity to infinity. The range is above 0. Notice you never have any negative y values. Remember, the domain is all your x values, how far left or right you go. Your range is all your y values, how far up or down you go. Here, your range is never going to go below 0. Your y values are never negative. And in fact, your y is never 0. It's always just above 0. Okay, so the range is going to be from 0 to infinity. And again, since you're not including the 0, we're going to use the round parenthesis to show that you don't actually reach the 0. It's just everything bigger than 0. And there we go. Which is great, because if I ask you, what's the graph of 3 to the x? You say that one right there. And I say, oh, no, I'm sorry. I meant 13 to the x. Yeah, that one right there. Oh, I'm sorry. I meant 113 to the x. Yeah, that one right there. Because as long as your base is greater than 1, it doesn't matter what the base is. It looks like this. Likewise, if I asked you, what's the graph look like if I have 1/3 to the x? Oh, it looks like that right there. Oh, I'm sorry. I meant 2/3 to the x. Yeah, looks like that right there. Oh, I meant 1 over pi to the x. Yeah, right there. Doesn't matter how simple or complicated the base is. As long as it's between 0 and 1, your graph will look like this. If your graph is equal to 1, that's not exponential, so we don't worry about that. And if your base is less than 0, then that's something way more complicated than we will ever have to worry about. So we just don't we don't see those at all. Exponential functions are extremely useful to model things in the natural world. You will often see population growth. If you study biology, the growth of bacteria and viruses, the propagation of disease, that will expand along an exponential growth model, at least for a while. Eventually it flattens out a bit. But early on, it follows an exponential growth model. Exponential decay models how radioactivity works. Radioactivity has a half-life, meaning that every so often the amount of radioactive material is cut in half, and then in half again, and in half again, and in half again, just like this one. Every time you wait a certain period of time, your amount of radioactive material gets cut in half again and again and again. This is also useful outside of the natural world in something very man-made. It's useful in economics. When you talk about exponential growth and decay, that is a good model for talking about interest. Compound interest, and in particular continuously compound interest, will all follow these models. So whenever you talk about finances, in particular interest, but also anything that involves the accumulation of money like amortization, payments of loans, and things like that, that will also follow the exponential models. So that is it for this topic right now. If anybody has any questions, comments, or problems, please make a note of those and please reach out. And I hope everyone has a nice day.